So section 1, properties of ocean water. In this section, we're going to go through properties of ocean water, including dissolved gases, dissolved solids, salinity of ocean water, factors that change salinity, temperature of ocean water, density of ocean water, color of ocean water, and then how we end up with deep ocean currents. So our objectives are describing the chemical composition of ocean water, the salinity and temperature, as well as density and color of ocean water. So let's get started right away with properties of ocean water. It is a mixture of chemicals that sustain a variety of plant and animal life. Many of the things that we find mixed inside of ocean water include things like chlorine ions, different forms of salt, some minerals. Anything that is washed off of the land from runoff can end up in the oceans. We notice that the oceans are actually increasing in salinity, and part of that is because we get water that is evaporated. Well, we aren't taking any of the salts that are in the ocean back up into the atmosphere. They stay trapped in the ocean, and then we end up with the water going over land, precipitation coming down, running off, and pulling more salts into the ocean. So scientists describe ocean water by using a variety of properties, such as the presence of dissolved gases and the presence of dissolved solids, which is salinity, as well as temperature, density, and color. So carbon dioxide is a major component of ocean water. It's not as high of a component in our atmosphere. Remember, we talked about how in our atmosphere, the vast majority of the gases that are there are nitrogen, whereas we've got oxygen and carbon dioxide in smaller amounts. Whereas in the ocean water, carbon dioxide makes up the majority of dissolved gases. There's 60 times more carbon dioxide dissolved in the ocean than there is in the atmosphere. There's also other atmospheric gases that are present in small amounts. And typically, we can end up with these dissolved gases coming from streams, volcanoes, organisms, but the biggest contributor is the atmosphere. Just simply the atmosphere exchanging gases with ocean water. Temperature in dissolved gases. Gases dissolve more readily inside of cold water. So if we think back to the stuff that we did with salmon in the past, we decrease the temperature of the tank. What we start to notice is an increase in the amount of dissolved oxygen. And the same thing applies in our global oceans. Where temperature decreases, more dissolved gases are going to be present. Where the ocean temperature is much warmer, less dissolved gases occur. And so as temperature increases, ocean water is actually outgassing. It's giving off the gases to the atmosphere that it would otherwise have trapped. So oceans and our atmosphere are constantly exchanging gases as temperature either increases or decreases. We call our global ocean a carbon sink just because it stores so much carbon. As mentioned earlier, there's 60 times as much carbon dioxide in the ocean as there is in the atmosphere. And that carbon can be trapped for hundreds or even thousands of years. When we talk about the deep ocean, a lot of that carbon dioxide that's trapped down there, it's not going to outgas for a very long time. Ocean water is 96.5% pure water, or just simply H2O. Meaning that 3.5% of the mass of the ocean is made up of things like salts. We call these sea salts in general. They tend to give the ocean kind of that salty flavor that you get if you've ever gone swimming in the ocean. You get a mouthful of water and it tastes salty. These are our ocean salts. So here's a breakdown of the types of dissolved solids that we have inside the ocean. 55% is chlorine, 30.6% is sodium, 7.7% is different oxides, magnesium 3.7%, and calcium, we're getting a little bit smaller, somewhere in the neighborhood of 1.5%. And then we've got potassium and other minor salts. So the most abundant elements that we have found in ocean water, dissolved in ocean water, are chlorine, sodium, magnesium, sulfur, calcium, and potassium. Halite is like table salt. It's the rock form of table salt before it's been all crunched up to make the smaller grains that you use. And so as we get runoff over top of land, any of that halite can be dissolved inside water and then run out into the ocean. Chlorine ions make up about 85% of the ocean's dissolved salts. And then also there's some trace elements of minor salts as well. So we've talked about just simply runoff. Well, where do some of these dissolved solids come from? Some of them can come from volcanic eruptions. So runoff would include chemical weathering of rock on land, as well as chemical reactions between seawater and any newly formed seafloor. And so rivers carry about 400 billion kilograms of dissolved solids into the ocean. So they're moving a lot of material into the ocean. And as mentioned earlier, those elements get trapped in the ocean because in the process of evaporation, water is the only thing that's leaving the ocean and moving up into the atmosphere. The salts remain behind. Think about if you were to go outside and take a cup of water and dump it out on concrete or on a black smooth surface, and all of it evaporates up. You see kind of this ring of materials that's left behind. These are the salts or the other materials that have been dissolved inside of that water. They're left behind. The same thing happens inside of the ocean when evaporation takes place. So how do dissolved solids enter the ocean? Weathering of rock on land, volcanic eruptions, chemical reactions with newly formed seafloor. All of those are possibilities. Salinity is a measure of the amount of dissolved solids or dissolved salts in a given amount of liquid. Obviously, the difference between ocean water and fresh water is the amount of these dissolved salts. And we measure them by the number of grams of dissolved solids in 1,000 grams of ocean water. So we mentioned earlier 3.5% on average. Fresh water is less than 0.1% salt. And it's important to recognize this 3.5% can change. We can fluctuate from 3.3% up to 3.7% in the amount of salts that are dissolved inside of water. So thinking about different portions of the earth, we have some places where evaporation is really, really high. And so if we have places where evaporation is really high, we may end up with higher concentrations of salt. So salinity might be 3.6, 3.7% in areas where there's lots of evaporation. And then in other places, we might be lower just because there's a lot of input of fresh water and not as much evaporation in those areas. So this image right here just simply is showing different areas on the globe where we have variations in the amount of salinity. Notice the Mediterranean Sea. We're talking above a salinity of 3.74%. Or 37.4 per thousand. So we're talking about a fairly high salinity in this area. Why would this area have quite a bit higher of salinity than out here in the middle of the Pacific Ocean? And the same thing over here for the Gulf of Mexico. The salinity is much higher. Like we're talking salinities somewhere in the 3.6% range. And then in the central part of the Atlantic Ocean, we're still pretty high. Why would we end up with quite a bit higher percentages as far as salinity here versus in the Pacific Ocean? We're at the same latitude. So the amount of evaporation is going to be pretty much the same because we're getting the same amount of incoming solar radiation at that latitude, why would we notice differences in the amount of salinity in the ocean versus those two different places?
Mr. Winter?
Yeah.
Did you turn off the thermostat?
I did not.
Okay. If you will.
So Dale realized real early on that the amount of water might cause these differences. This small amount of water for the Mediterranean Sea, you're going to not have as much input into it. You're going to have more evaporation causing water to move out. Same thing for the Atlantic Ocean. A very small space comparative to the Pacific Ocean. There's just a lot more water here to create differences in salinity. Temperature of ocean water is also dependent upon a number of different things. Depth of the ocean can be part of this. We talk about very deep sections of the ocean. It's going to create temperature differences versus shallow areas with lots of solar radiation inputs. It might be slightly warmer or quite a bit warmer. And then also inputs of fresh water near to the poles or freshwater inputs from rivers or streams might change temperature as well. So the range of ocean temperature is affected by the amount of solar energy in an area, but it also could be inputs of other things. So this map right here is showing those differences in temperature. It's showing that along the equator we're having a lot more input of solar energy, whereas near the polar regions we're having less solar energy input, and so our temperatures are quite a bit lower. Do we have any questions about that? So this is just specifically showing surface temperature inputs. So our surface temperatures are higher, whereas if we're talking about the deeper sections of either the Atlantic or the Pacific in these two oceans, we might have temperatures that decrease quite a bit. So we're just looking at surface temperatures here. We're all familiar with the fact that as we make our way towards the poles from the equator, the amount of incoming solar radiation changes, right? And because we have changes in this amount of solar radiation, we have differences in temperature. Pack ice is a layer of ice that sits on top of the ocean, specifically in our polar regions. It is usually no more than 5 meters thick. And typically it will prevent the water that's down below from freezing. Oftentimes, because we have higher salinities in these areas, these higher salinities lead to the water down below not freezing. So it kind of insulates the water that is below. Think of every winter, and you go get salt for on top of your driveway, right? And that salt, in a range of temperature, will allow the ice that is created to melt, right? The same thing's happening inside of our global oceans. When we have higher salinities, there's going to be less freezing that takes place, within reason. When we get below -3 degrees Celsius, that salt does not work anymore. And so if we get colder than that, we're still going to get ice formation. So what factors affect the surface temperature of the oceans? What's that, Avery? Density is definitely a factor. What else is going to affect surface temperatures?
The sun.
The sun. Inputs of solar energy, right? So near the equator, we have larger amounts of inputs of solar energy. As we make our way towards the poles on both sides, we're going to have less inputs of solar energy, and so temperatures are going to decrease. And that's going to lead to differences in density too, right, Avery? So as we have differences in the amount of energy, remember in the past we've talked about these particles being excited when we're getting energy, the little lumps moving around more and more and more, the more energy we have, well, that's causing density differences, right? If those particles that are making it up are spread out, then our density is going to go down. If they're closer together, our density increases. So surface ocean temperatures are affected by the amount of solar energy and by the movement of our ocean as well. The thermocline. The thermocline changes throughout seasons. Changes based on the amount of solar energy. So oftentimes when you hear like some of our Great Lakes fishermen, they go out and they take boats out into Lake Michigan, and they like to put their baits right at the thermocline. And depending upon the time of year, that thermocline might be closer to the surface, or that thermocline might be deeper down. Mr. Hungerford was in the other day, and he was talking about going out on Lake Michigan with a charter and going fishing, and they were doing really well. Oftentimes, these fishermen will go about trying to put their baits right at that thermocline because the bait fish, they like the warmer water that's up higher. And the larger salmon that oftentimes we're targeting in Lake Michigan, the temperature that they like is quite a bit lower. And so they'll hang out below that thermocline. The bait fish will hang out above the thermocline. And so by putting your bait right at that thermocline and kind of running it through it, the salmon will kind of come up and they'll eat it because that's what they're doing. They're actively kind of looking up, looking for food to eat. So the thermocline is something that is important to an entire industry, fishing industry in our Great Lakes. It's also important to our commercial fisheries in our oceans. Our commercial fisheries are actually going about trying to figure out where this thermocline is in order to figure out where they're going to try to net for fish or they're going to try to catch fish. So the thermocline is a layer in which the temperature drops very quickly, and most of the time it's due to incoming solar energy not being able to go any deeper. It exists because the water near the surface becomes less dense as energy from the sun warms that water. And so it's a distinct difference, it's a distinct separation between warm surface water and the cold underwater. All right? Deep ocean water. In the deep zones of our ocean, our temperature can actually get below freezing. Okay? It does usually kind of stay 2 degrees Celsius. Remember, 0 degrees Celsius is freezing on the Celsius scale. 2 degrees Celsius is slightly above it, but we can actually get deep ocean water that's down around -3 degrees Celsius. And so it's very, very dense, and it's usually has high salinity. It also helps to hold lots of dissolved gases. So we talked earlier about the amount of dissolved gases in colder water is going to be far higher than the amount of dissolved gases in warmer water. We've talked a lot about density, and density being the ratio of mass to volume. And typically we express that in grams per cubic centimeter. We continue to do the same thing in ocean water. We can talk about grams per cubic centimeter of ocean water regarding density. What happens to a material that has a higher density? Let's say our grams per cubic centimeter of this ocean water is 1.1. And then we've got another amount of ocean water that is 1.0. We've got 1.1 and we've got 1.0. What's going to happen to the 1.1 grams per cubic centimeter water comparative to the 1.0 when we're talking density? What happens to a higher density material when we're talking about liquids? So 2 factors that affect density of ocean water include salinity and temperature, and dissolved solids, which are mainly the salts, add mass to that water. And so that's why we end up with differences. Okay? So this right here is just showing that that bottom water that's denser, that surface water that's less dense. We're not getting mixing that's taking place as you guys brought up. So ocean water becomes denser as it becomes colder and less dense as it becomes warmer. And so we end up with temperature affecting the density of ocean water. And it happens more than salinity does. So the densest ocean waters are found in polar regions. Our less dense ocean waters are found in our tropical regions. So why does ocean water, why is it? So ocean water contains dissolved solids, mostly salts, that add mass to a given volume of water. Color of ocean water gives an indicator of overall ocean health. So we have phytoplankton that are growing inside of ocean water, and that tells us a little bit about how healthy that specific area is. That phytoplankton then either absorbs or reflects light. As sunlight penetrates through the surface of the ocean, it's absorbed by the water. Some of it is reflected off. Only the blue wavelength of light tends to be reflected, which gives our oceans that blue color that we're so familiar with. I threw a bunch of pictures on here. We can see difference is in color here. So this one over here is more of a blue color. Way back out on the horizon, this one's really kind of dark blue, whereas near to the surface, we're seeing a little bit more of a teal or a green color. Substances in the water or organisms themselves can give ocean water color. And so that can be an indicator of the amount of productivity that any particular area is having. Is it really productive for creating phytoplankton that lead to the base of our food chain? That might be a good indicator to say that's a healthy ecosystem. And so all of these things can affect the color. Phytoplankton tend to absorb red and blue wavelengths, but they reflect green. And so when we have phytoplankton inside of a body of water, they're absorbing nutrients, and that the presence of those phytoplankton can indicate whether it's healthy or not.